Hi, in this video we're going to work through the exercises related to logarithms. So getting started right away, if you need to, you can type these into your calculator initially, but we saw in the video that the log of something raised to an exponent, the exponent comes out, so we'd have -6, and then all we'd have left is the log of 10, but we know the log of 10 is 1, so we'd have -6 times 1, so this equates to -6. So again, to be faster, more efficient problem solvers, getting used to just seeing something like the log of 10 to whatever is that whatever. So by that logic, log of 10 to the fourth is going to equal 4. So we shouldn't really need a calculator any longer for something like log 10 raised to something else. Now, this one is the natural log of 27. This one you do need a calculator for. And then when you calculate that, you get 3.296. And I see here that it must really equal that because I've got two equal signs. My apologies for that. And then the log of 27, if you type in that into your calculator, you get 1.431. Now notice here we're taking the natural log of one number and the base 10 log of that very same number, and you do get different results. And we saw in the video that there's a relationship between base 10 logs and natural logs. I always forget that what that relationship is, whether it is 2.303 times the natural log is equal to the base 10 log, or if it's 2.303 times the base 10 log is equal to the natural log. But if I pick any number, I can generate that result. So we could check 2.303 times the natural log. Well, the natural log is 3.296, and ask, does that equal the base 10 log, 1.431? Well, it's pretty clear 3 times 2 is 6, and that's not going to equal 1.4. So right away we can strike that, and then we could verify that 2.303 in fact times 1.431. If we take that and do it on a calculator and see what we get, we in fact do get 3.296. So we know that this is the correct relationship. Furthermore, even if we forget the 2.303, there's a way to generate that. If we look at these two numbers, if we take 3.296 and divide by 1.431, we get our missing conversion factor. So if you go ahead and do that on your calculator, I guarantee you're going to get 2.303. And then we could say, hey, look, this was the log, the natural log of our number. This was our base 10 log of our number. So now I'm getting a little crowded, so I'm just going to hop up here. So now we can broaden this and say, this must be true. And then if we cross multiply by log x, we would just be left with the natural log of x is equal to 2.303 times the base 10 log of x, which is exactly what we convinced ourselves must be right. So simply by picking two numbers and taking the ratio of those two numbers, seeing what gives us that 2.303 will allow us to derive this relationship. So I don't have that one memorized. I just always generate it when I need it. Now, 6, 7, 8 ask us to follow the rules of logs. Not so interested in the actual number. We could clearly take 36 times 43 in our calculator and then take the logarithm of that result. This is more about extrapolating from what we do with numbers to doing them with symbols. So here we saw in the video that anytime we have two things multiplied by each other, this is the equivalent to the log of 36 plus the log of 43. So if we were to calculate what that number is, add it to the log of 43, we would get the log of the product, 36 times 43. So again, notice that these parentheses are key because it really helps us figure out what is being taken the log of. That's a terrible English sentence. What are we taking the log of? Everything inside the parentheses. Broadening this to symbols, we would have log of A plus the log of B. Everything to this point has been two things multiplied by one another. but it does clearly extend beyond that. So this would be the log of A plus the log of B plus the log of C plus the log of D. So any number of things multiplied by each other, we could just add the individual logarithms together to get the final result. Broadening this into something even nonsensical now, the log of the quantity albatross times coconut would be equal to the log of albatross plus the log of coconut. I must have been watching too much Monty Python or something when I was developing this sheet. Now we move on to division. We saw that when we multiply two numbers together inside a logarithm, we add the individual logs together. The corresponding mathematical relationship for division, it would simply be subtraction. So we take the log of the numerator minus the log of the denominator. And again, I like to use a lot of parentheses. The log of g over 2 would equate to the base 10 log of g minus the log of 2. Here we have the log of y times z over a. So if I rigorously take the numerator is y times z. So it would be the log of that quantity minus the log of a. But now we can also rewrite the log of y times z as the log of y plus the log of z. And that would be that whole quantity, because that is what's coming from this, which is coming from the numerator, minus the log of a that we still had over there. So we can actually break that up quite significantly. And what we're going to see on the next page is that doing that is going to help us figure out complex numbers if we're stranded on a desert island without a calculator, but if we brought our logarithm table of the logs of the numbers 0 through 10, or 1 through 10. Take the log of any number greater than 1. So pick a number, doesn't matter how big, take the logarithm of it, positive or negative. When you did this exercise, you should have found that you got a positive number. And notice that I said when you did this exercise. I really hope you're taking the time to do these for yourself. The experiential learning that you get by physically doing these things yourself will make this stuff stick a lot more than me just telling you that these things are true. If you experience it for yourself, you will never forget it. Whereas if I just tell it to you, probably by dinner time, if you're watching this in the morning, you might not remember the results. So you got to see these things for yourself. It's a tactile sensation. Repeat this 4 more times. With any number greater than 1, you will always get a positive value when you take the logarithm of a number greater than 1. If we operate with decimals, something that is less than 1, like 1/4 or a half or 0.0000000097, you will get a negative number. And that will always be true for decimals less than 1. So you get a negative. Notice what happens if you try to take the logarithm of a negative number in your calculator. What do you get? Okay, moving on, the next page starts with this table where the log of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are all presented. And I'm going to show in this exercise that what people used to do and why logarithms were so valuable is that if you memorized these, if you knew, for instance, that the log of 6 was 0.7782, and you didn't really sit down to memorize them, they became like telephone numbers in that you used them so often that you knew them. You can generate the logarithm of any number that you can really dream up of, as long as you could break it up into smaller numbers. So what do I mean by that? Well, let's even look at the log of 2 and the log of 3. The log of 2 is 0.301. The log of 3 is 0.4771. So let's imagine that I knew those two things. I had those memorized, 0.3 and 0.47 even. Just rounding it. Now I want the logarithm of 6. Well, I don't know the logarithm of 6. But I do know that 6 is equal to 2 times 3. And like we just saw on the previous page, we know that that's the log of 2 plus the log of 3. Well, now I'm in luck. I know that the log of 2 is 0.3. I know that the log of 3 is 0.477. So if I add those two things together, I get 0.777, and I'm at least in the ballpark of what the right answer is going to be for the logarithm of 6, which is 0.778. So yeah, I didn't have the 0.301, so with rounding, this should be 0.778. But to 2 decimal places, I was right. To the third one, it was very close. So without a calculator, you could still do logarithms if you knew some of the, or if you knew all of these from 0 to 9. Okay. And I encourage you to do this with, a few others. I say here, just 2 times 5 works. So if you had the log of 2 times 5, well, that should be the log of 10. Well, we know the log of 10 is, the log of 10 is not 0. The log of 10 is 1. I will fix that as soon as this video is over. The log of 10 is 1. So we could rewrite this as the log of 2 plus the log of 5. Well, the log of 2 is 0.301. The log of 5 is 0.699. If you add those two things together, you get 6 and 3 is 9. 9 plus 1 is 10. So all of this would tick over to 1.00. Okay. So in fact, you don't even need to know the log of 10 is equal to 1 if you know the log of 2 and the log of 5. Another way, or another example here that I asked about is the log of 9, right? You could get 9 by saying 3 times 3. Okay. So 3 times 3 can be rewritten as 3 squared. Or we can just leave it as 3 times 3. Either way, note what happens here. If we leave it this way, we get the log of 3 plus the log of 3. Well, that is just 2 times the log of 3. Remember what we did with exponents and logs? We brought it outside and we said this is 2 times the log of 3. Exactly the same result regardless of how we treat it because they're all mathematically equivalent. And now if I know the log of 3 is 0.4771, I take 2 times 0.4771. And again, we don't need a calculator to do that. We take 0.4771 times 2, we get 2, 14, 14, 15, 8, 9, 0.98542 would be the logarithm of 9, which is that. So by knowing a few of these, having a few of those memorized, then other logarithms can be generated. Okay. So now let's extend that to numbers greater than 10. So again, the challenge here was not to use a calculator. So using only the table above and the rule of logs, what is the log of 20? Well, a couple ways to think about this. You could think of this as the log of 20 is the equivalent of log of 4 times 5. Log of 4 times 5 is the log of 4 plus the log of 5. Log of 4 is 0.6020. The log of 5 is 0.6990. And if you add those two things together, you would get 1.301. You could also go about the log of 20 as the log of 2 times the log of 10, which is the log of 2 plus the log of 10. This is probably the way most people would do it because we like the log of 10 because we know what the log of 10 is equal to. The log of 10 is equal to 1. What was the log of 2 equal to? 0.301. 1.301. So we can calculate the log of 20 as being equal to 1.301 without even needing a calculator if we just know a few of the logs early in the number scale. Okay. So this is a great little bar trick. You could probably make some money in a fraternity or sorority by challenging people to say, hey, give me a number and I'll take the logarithm of it in my head and I'll get to within plus or minus 0.1. And if you know these, right, you certainly can generate the correct logarithm. Okay. So the log of 32 you could think of as, well, you could propose a couple different things here. You could maybe think of 32 as 16 times 2. Well, we still don't know the logarithm of 16, but we do know 16 is 4 times 4. So you could say this would be the log of 4 times 4 times 4, which is going to be the log of 4 plus the log of 4 plus the log of 2. And then you could look this up. So it would be 0.602 plus 0.602 plus 0.301. Or this is the log of 8 times 4. The logarithm of 8 is 0.9031 plus the log of 4 is 0.6020. You add those two things together and you get 1.505. And now, just because this might be new to you, I would then go back and say, okay, now take your calculator, punch in log of 32. Do you indeed get 1.505 as the answer? And you will, guaranteed. Log of 25, we might recognize 25 as 5 squared. So here again, we invoke the rule that this becomes 2 times the log of 5, which becomes 2 times the log of 5 is 0.6990. So you just take 0.6990 and multiply it by 2. In a lot of people's worlds, 0.699 is very close to 0.7. So you could say 0.7 times 2, 1.4. Okay. That 1.4 is 1.398, but 1.4 is a darn good guess for not having to do any computer or any calculator work. Log of 9 squared for 81. Here again, you would say that the 2 comes out. We get 2 times the log of 9, 0.9542. And you get 1.9084 for that. So I personally find this actually rather fun. Once you kind of catch on to this game, you can really pick just about any number. Certainly if it's a number divisible by 2, you can start hacking it down and saying 2 times this times this times this and get quite far. The log of 1,000, now here we might recognize that this is equal to the log of 10 cubed, which is equal to 3. Well, let's say we didn't recognize that, but we do know that 1,000 is 10 times 10 times 10, which is why it's 10 cubed. Well, that would equal the log of 10 plus the log of 10 plus the log of 10. But what's the log of 10? That's just 1. Plus 1 plus 1. So again, any way we slice it, we get 3, because 10 cubed, 10 times 10 times 10, and the log of 10 plus the log of 10, they're all mathematically equivalent to each other. So of course we have to get the same answer. Log of 8,000 then? Well, we could think of the log of 8,000 as the log of 8 times 1,000. Well, we know 1,000 is, well, should rewrite this as the log of 8 plus the log of 1,000. What's the log of 1,000? It's the log of 10 cubed. It's 3. We just calculated that. So I'm going to say I don't know the log of 8, but I'm going to add 3. And the log of 8 is 0.9031. So the total here is going to be 3.9031. And notice any number that's 6,000, 7,000, 8,000, anything that's between 1,000 and 10,000 is going to fall in this range of 3 plus a decimal. If we had 4,000, it would be 0.6020 plus 3, or 3.6. If it was 5,000, it's going to be 3.69. If it was 6,000, it would be 3.77, because we'd have 6 times 10 cubed. So anywhere between 1,000 and 10,000, we're going to get 3.4, 3.6, 3.7, 3.78, 3.84, 3.9, 3.95 for 9,000. Now we can do something crazy, not crazy, perfectly rational, like 160,000. Well, how are we going to get 160,000? Any way you want to dream up. You might initially recognize this, and when I wrote this, I was thinking it's the square of 400. If you take 400 times 400, you'd get 160,000. Well, how do we write the log? I'm going to turn this over, give myself a little bit more room. The log of 400 squared, okay, that's going to be 2 times, because remember the 2 comes out. That gets us log of 400. Well, that's going to be 2 times, and notice here the liberal use of brackets and parentheses. This is the log of 4 times 100, which is 2 times the log of 4 plus the log of 100. Do I know the log of 100? Yeah, that's 10 squared, that's 2. And then I'd have to look up the log of 4, but if I had my handy dandy table, 0.6020. So now the internal part, the 400 part, becomes 2.602, and then we still have the 2 hanging out there, which makes this 5.204. So 4, 0, 12, 4 plus 1 is 5, 5.204. Okay. And I guarantee if you take out your calculator and you punch in that, you will get 5.204. And here again, notice if we were to write this, we'd get 1.60 times 10 to the 1, 2, 3, 4, 5 log 1.6 times 10 to the 5. Notice this 5 and that 5. So we've got a number a little bit greater than 1 times 10 to the 5th. If we had the log of 1 times 10 to the 5th, that would equal 5. Because we have a little bit more than 1 times 10 to the 5th, we're going to get a little bit more than 5, 5.2. Challenge you to take something like the log of 8.3 times 10 to the 5th. What do you get? Take out your calculator. I get this is equal to 5.92. So notice here again, magnitude of 5, that 5 is coming from that 10 to the 5th, and then the 0.92 is coming from the 8.3. Notice 8 is 0.45, 9 is 0.95, 8.3 is somewhere, I'm sorry, 0.90 and 0.95. 8.3 is somewhere between those two numbers, 0.92. Okay. So once you understand or begin seeing where the actual answers come from in logarithms, I think it kind of demystifies them a little bit. So I hope this is helpful to you as you're working problems that require the use of logarithms. You know, I hope this comes back and you can at least check the order of magnitude of your answer and start seeing trends in logarithms and looking for patterns. Thank you very much and have a great rest of your day.